Okay, this is the solution for exercise 3.12, one of the grad student-only problems, and it asks us to prove part B of theorem 3.4. Right, so here it is. If the first derivative of f at the point x naught is 0, and if the second derivative of f at x naught is greater than 0, then x naught is a min of f. Okay, so we got to prove that. Okay, so to prove this, we're going to start with what the first derivative of f at point x naught equals 0 implies, right? Well, that implies that the tangent line of f at the point x naught is horizontal, okay? And so this implies that either x naught is a min of f or that x naught is a max of f. The second assumption, that the second derivative of f at x naught is positive, basically means, there's different ways you could do this. You could take the approach of the book and try to just use words, which is totally fine. I tried to take a more notational approach, okay? So mostly for a learning opportunity, but here's a symbol that I don't think I've shown you guys yet. This basically means that there exists, okay, so what this says is that there exists an epsilon greater than 0. Here's another one we haven't seen yet, such that, okay, so there exists an epsilon greater than 0 such that the first derivative of f is increasing. It's an increasing function on some interval x naught minus epsilon to x naught plus epsilon. Okay, so basically the restriction here is that epsilon is positive, so this is going to be a number smaller than x naught, and this will be a number bigger than x naught. So this is a totally valid interval. And basically what we're saying is that there is some epsilon, right? There is some epsilon, not all epsilon greater than 0, but for some, this is true, okay? All right, now since the first derivative of f is an increasing function on this interval for some epsilon greater than 0, and because the first derivative of f at x naught is 0, meaning the tangent line is horizontal, and that this is true, well, that implies that for all delta less than epsilon, so basically for any point on this interval is kind of what we're saying here, for any delta less than epsilon, the function f evaluated at x naught minus delta, so some number smaller than x naught, but bigger than x naught minus epsilon, the function is greater than it is when it's evaluated at x naught, right? So in other words, any number to the left of x naught, to a number that's smaller than x naught, that's in this interval, is going to be bigger than this, right? Okay, so at least from the left side, this is looking like it might be a min, right? Now, when we add to that statement, and also on the other side of x, right, the sides where x's are bigger than x naught, it's also bigger than f at x naught. So since this is bigger than f at x naught, and this is also bigger than f at x naught, then this has to be at least a local min, perhaps even a global min. But we don't have to prove that. We just have to prove that it's a min of some kind, right? And that's what we prove. All right, so for exercise 3.18, we're asked to prove that the point elasticity is -1 exactly at the midpoint of the linear demand in figure 3.20, which is right here. Okay, so all we're really going to need is that the midpoint value for price is A over 2B, And we also need the function, because we're going to use this formula right here for the price elasticity. All right, so the point at the midpoint of the demand line, capital F of P equals X. So here's the demand line that we just saw. So this function equals A minus B times P. There's the midpoint, right? There's the P value, there's the X value. We don't really need the X value, but I went ahead and made the point explicit anyway. All right, so we know that the point elasticity is given by this equation. And so if we take the first derivative of the function with respect to P, we get negative B, and then times P, all over the function itself, right? So divided by A minus B times P. And since P equals A over 2B at the midpoint, the point elasticity at the midpoint is simply the equation we just derived, evaluated at price equal to A over 2 times B. So we just plug those in for P, for our P's here. Okay, and simplify. So the B's cancel out, and we're left with negative A over 2. And then the same thing happens here, so we're left with A minus A over 2. And A minus A over 2 is just positive A over 2. And that, of course, is just negative 1.